No, I think they're like boring. I think they're gonna be like November.
One of them weird that design.
I saw one of them once there. You walked right past me and just not. They also drove 5 minutes. That's wild.
It's a little creepy.
Why is that creepy?
You just know that. It's like I kind of when I drove over there.
Yeah.
They're like, or back to that.
A whiteboard.
I know you.
All right.
So I'm now. You have to. If you need help consulting, you can ask me.
No, I like the guy. See, he's nice.
Or download the files off your desktop.
Yeah.
Do it properly.
I like what this guy.
That's all I did. I literally just slapped on my list.
All right, let's go and get started. How are people doing on WaveWriter analysis? Any joy? All right, everyone understand what we're looking for in the way of plots? The I don't know if the wording too ambiguous. Last time people were super confused. So you're computing lift and drag coefficients in L over D for the different conditions. And so what I'm looking for is something like CL and the sum curve. And then there's going to be alpha and CL. There's going to be some curve. So I don't think there's a reasonable way to merge the two. So anyway, that's about it. Shouldn't be too horribly hard. You could probably get CLCD in the same plot. Right. That like almost shows up. Anyway, hopefully it's not too bad. All right, so let's see. There's just a couple of sections we still want to cover in the book. The chapter, I think it's 7 in Latzer's book, he calls higher order methods, and it's pretty brief, but maybe we'll just talk about it for a second. Going back to potential flow again. Small disturbance approach. And I think he writes we had that generalized equation, like 1 minus m squared dxx plus dyy equals 0 for compressible flow. And if you remember, we introduced it, we said this works pretty well subsonic and it works pretty well supersonic, but any place around sonic is problematic. This term pretty much vanishes. I think there's actually a 3D variation when plus z. And then if you're near sonic, this whole term gets quite small. And what you have left, this is the streamwise direction. It's basically saying that this term kind of vanishes and you're left with a 2D problem. And it's a plane that's orthogonal to the free stream flow. So you're really solving for cross flow velocity at that point. So not too far off from what we were doing just previously with super simple methods for attacking the super slender bodies and slender wings. And there's one other thing, just throw it up there because it has some historical relevance to myself. There's a version, a 2D version of a marker that's still right. 1 minus m squared dxx plus 5 volts. gamma plus 1 times dx times x. So this is actually a non-linear version of the 2D problem. We call it the transonic small disturbance. Pretty. It was pretty common when I was a student. In fact, my first graduate CFD class, that was one of the projects we had to do was solve this. It's nonlinear, which means it has to be an iterative solution. So we basically would take a domain and we'd limit it to super skinny wings, kind of like all of our linear perturbation theory. So we have some kind of a piece of wing here. And like we did with the small disturbance analytic solutions, we would ignore the fact that there was actually thickness to this, but we would include the fact that it was producing a little delta v, little tiny v prime vertical velocity. And so you could plug that in, and then you'd end up, you could actually do supersonic cases, shocks, expansion bands. And so it'd be a mesh. You have like 0, boundaries, and then solve for it through the whole thing. So when I was a student and did this, we had they're called mainframes. Anybody know of a mainframe? So this back when nobody had a computer sitting on their desk. So some large, very air-conditioned room in the building would have a computer about the size of this room that had about a millionth of the power of phone. Anyway, so it would take it maybe 10 minutes to run that. And then after I got here and the internet became a thing, I wrote a little web program that would solve this as a web page. And on the server, which was like a Pentium Pro 2, I think, 400 megahertz or something, it could generate the graphic image for that in about a second, maybe. Anyway, I don't know if anyone still does this. I think it's lost its value. All of this stuff, these methods kind of led to like the method of characteristics, which again, I don't think people use very often. It was a big deal when aircraft started to fly, commercial aircraft in particular, started to fly transonic wing, and you're starting to get a supersonic region. You pay a drag penalty for this, and so the Boeing and Lockheed and everybody else would try to figure out how can they modify the top of the wing in order to minimize this. And so they were running potential flow out here in this whole region, and then inside of here they do this method of characteristics, and they would slowly, essentially tweak the shape of the surface. Usually it got flatter to try to shrink that supersonic region and make the shock weaker. But again, I think with Navier-Stokes now, I think that's not super common. There was a student here, actually, I don't know, a couple of years back, 3 or 4 years ago, that used the method of characteristics to design part of the nozzle in the supersonic wind tunnel out there. Got that road. It's basically this back region here. So here's your test section, airfoil, whatever. And this is subsonic and supersonic. And we did quasi 1D analysis through here just to figure out how to get the right Mach number back here that we want. And the question is, when you do this and it's not technically quasi 1D, it's really 2D or 3D, what's the distribution of Mach across here? Is it uniform? Boundary layers for sure, but do you have some messy distribution of mock across there? And so I think they use the metric characteristics in here to shape this in order to get as uniform a mock number as they could. So it turns out the shape of this affects that distribution. Anyway, I think that's about all he has in his higher order schemes. The next bit, I think it's chapter 8, is interesting, and it's what we're going to do for the last homework problem. And it goes back to all about kind of vortical flows. So you guys did homework for the vortex lattice method. So we're looking at wings that have these tip vortices coming off of here, and actually a distribution of shed vorticity all the way across. And that all worked great. But it's that theory never predicts the stall of the wing, right? I don't know, probably nobody tried it, but you get a value of DCLD alpha. And so you're just multiplying by alpha to get CL at whatever angle of attack you want. So put in 90 degrees. You're going to get something close to 2 pi. And you're not going to get that in real life. That's not going to happen. So in real life, that wing is going to stall. And stall is an interesting thing. It can happen different on different airfoils. If you start slowly cranking this angle of attack, some airfoils are going to have stall that starts at the trailing edge and slowly creeps forward. And so it's, I would say, graceful. It gracefully degrades the performance. So nothing abrupt happens, and you kind of get a feel that your wing is starting to fail and back off. Other airfoils, the stall just goes from completely attached to suddenly stalling way up here near the suction peak. And that's problematic because you get a warning, you got great performance, and then suddenly you got nothing. And even more interesting is that when it happens, if you remember that video we showed of the two airfoils, one was laminar and one was turbulent. And it's a trick question because it looked like the laminar one was actually turbulent. So it turns out that stall actually, it takes some amount of time that happens. If you were to crank this thing to an angle of attack, what you'll see is a big separation bubble will form, and it'll get bigger. There's like a vortex that's stuck in here. And I don't know if this is completely accurate, but one way to interpret this is that you've got bound circulation inside the wing that's creating the lift on the wing. And some of that circulation goes into this kind of big separation bubble here. It's like a big vortex that's churning in here. And it grows over time. And at some point, it kind of separates from the wing and then eventually goes off on its own and travels downstream. Up to the point where it separates, this wing still produces great lift. In fact, the lift can actually improve with the addition of that vortex that's pasted onto the leading edge. Once it separates, that wing's done. The lift plummets. You're finished. So there's some interesting things that come out of this. Helicopters actually suffer from this problem cyclically, right? Every time the blades go around and you're in cruise flight, they're going through angle of attack changes. And so they're generating these, and then they shed and recover because it goes back to the angle of attack. So there's actually like a hysteresis that alpha and CL, you get some kind of a loop. So when it's just starting to stall, it's on the high branch, and after it's stalled, it goes on the low branch while it's recovering. So there's a lot of work going into helicopter stuff to try to analyze that. In nature, this same thing comes back all the time. You hear all these arguments about how bumblebee can't fly, right? you look at little micro wings, they just, if you try to apply your linear arrow knowledge, it's not gonna go, it's not gonna work. So they're surviving on this. So the lift can get quite high as long as that's attached. And what they do is they've got the timing down so that by the time that starts to separate, they quit a stroke and they reverse and go back. So they're surviving on a vortex attached on this side and attached on this side. The timing becomes a critical thing. They can do other cool stuff. If you actually look at something like a dragonfly wing up close, they don't look like an airfoil that you would see. They're all totally jagged and random. All these little veins out here that stiffen them up, membranes in between, and they can even be broken, they can get missing chunks of the wing, whatever. And what happens is you get little vortices that get trapped in all these little pockets. And so the outer flow comes and flows over the outside and looks more like a wing that we're used to. So that's how they survive, super low Reynolds number. Anyway, doesn't apply for missile stuff, but there's some interesting things that do apply. So we were looking at finite wings that were unswept. So, and you, in your vortex lattice method, guys, I think pretty much everybody did some things where the wings were swept pretty far. And one thing that the vortex lattice method misses is that if you sweep the wing far enough, so delta wing here, so it's flow coming in, you're getting this bound circulation stuck on the airfoil here. And if the wing sweeps far enough, there's really sort of a vortex filament that goes through there, and you actually get flow that goes in that direction. So this vortex actually gets quite strong as it goes outward. And it turns out that it's sort of self-maintaining. Unlike the unswept wing, where that vortex would grow to a certain size and give up, depart. On the swept wing, it does not. It stays there. And so it sits there churning away. And what happens is it's taking high-speed flow out here and it's bringing it back into the boundary layer. And it prevents the boundary layer from ever stalling. Not ever, but you can get to amazingly high angles of attack without the flow stalling on the upper surface. So, and they call it vortex lift, and you can get some interesting stuff out of it. Bring up Platzer's books. He's stolen some pictures from somebody. I can throw in there. Let's see. Let's see. Let's see. This is Van Dyke stuff. Oh yeah, there's some other vortex things that play a role in missile design. I think we talked about it briefly, but if you have a body of revolution at some angle of attack, you get that cross flow velocity, and the cross flow velocity looks a little bit like flow over a cylinder. And you remember from flow over a cylinder that you get a vortex streak coming off of the back. So you get the same thing off of missile bodies. They can be shedding a vortex off of each side, and they can actually start to be asymmetric. So that's the kind of problem where if you tried to run a CFX simulation and you cut this problem in half and put a symmetry plane in, you would prevent the possibility of there being asymmetry. And that may corrupt the actual lift and drag values that you get out of it. Let's see, they even go up into supersonic flow, Mach 1.6. But again, the crossflow velocity is kind of what matters. It's what's forming those vortices, and the crossflow velocity is under Mach 1. So you can still get them at supersonic speeds. The place where this kind of oscillatory behavior would probably get you would be on controls, right? Because you're getting like side loads. It would be periodic at some high frequency, whatever the shedding frequency is. So if you tried to have a control system, you'd have to somehow filter that out. You don't want to react to. Let's see what else. So here's the delta wing. So here's a kind of a extremely classical picture. So here's the vortices that come right off the point at the front, one on each side. And we'll look at some CFX data here in a little bit, but what you'll see is that there's like a huge chunk here that probably would have been separated at that angle of attack. This is, I don't know what the angle of attack is here, 15 degrees. Okay, so you guys will do this. Oh no, that's the semi-vertex. It's 20-degree angle of attack. So normally, if this was an unswept wing, it would totally be stalled, be useless. But for with the swept wing, these vortices reattach the flow. You can sometimes have a pocket in the middle that's separated, because the effect of the vortices doesn't reach super far. So certain angles of attack, you'll have some regions that are good, some regions that are not. And let's see, here's a side view of it. They're cranking like this, so they're actually throwing material down on the top of the wing in the middle here. That might be all he's got. And I think Platzer has. This is useful. Let's see. So here's lifting surface, some experimental stuff, and then this is, let's see. Oh, I'm sorry, that's still back when we were looking at this slender body. Sure. Yeah, you can tell where that figure came from. Figures from Hasno. Yeah, here we go. So here's this dashed line is basically what you would get from vortex lattice method, which you guys are going to do for the last homework assignment. It's just linear, right? All you get is one value of DCLD alpha, and you assume it's forever. And what's interesting is that you can actually achieve better than that once you add in the vortices from the highly swept wing. So what you're doing is you're actually down in this region. You're actually still higher than linear, at least for reasonable angles of attack. I think our case is aspect ratio about 2.8. Anyway, so you guys can actually do this comparison out of that project. This is all subsonic. All these vortical structures. Once we go supersonic, all that goes away. And now each section of the wing is sort of independent. You can almost use like a strip theory approach, where you do a 2D solution on each strip, and add them all up. There's not entirely true. On the lower surface, you'll see there's some flow that starts to wash out for on the inside, some washes. It's nearly separate. And then you'll just get a big shock off the top. I'm sorry, off the bottom, big expansion wave off the top. Anyway, so what's another thing that's quite interesting is that subsonic, you would typically never find anybody making a sharp edge on anything, just because the stall characteristics are miserable. If you think about, you have a diamond airfoil, and in subsonic flow, when you start to put in lift, what usually happens to the stagnation point in front? Got some streamline that comes up. On a normal airfoil, you watch it travel down underneath the lower part of the wing, right? What happens here when you got this sharp bit? Well, I think it's still going to try to travel down here, but flow is going to not want to turn that corner. And, so typically, sharp leading edges are super bad for low speed flight characteristics, unless your wing is super swept, and then whatever stall would normally occur in a 2D section goes away because of the sweep. Most supersonic aircraft that we fly, super sharp lead edges because they work better in supersonic flow, but they're all swept, so. And then for landing, they'll try to match this pretty close to the incoming flow to try to help it out. for, landings. Yeah, anyway, so there's some interesting things. You'll see all of this stuff when you do your CFX. I think I have a couple of the solutions here we can take a look at. And I'll tell you, I did just post the assignment. I don't know if anyone saw it. I just posted like an hour ago. When I did that one, let's see, I can here. See it. I think when we did it last time, this is where we kind of discovered that trick with gamma and the real gas with specific heat constants. And then the subsonic case that you do, that'll work just fine. In the supersonic case, it will also work, but it will converge quicker if you don't do that. So if you actually look at the if you look at the RMS behavior, these actually do cause some grief in the supersonic case. So if I were you, I think I threw it a note. Yeah, if I were you, I would swap them out for hard numbers, and then the convergence would be a little bit quicker. They all converge pretty fast. You need to do a handful of angles of attack. I think you do 0, 5, 10, and 20 degree angle of attack at Mach 0.5 and Mach 4. Let's see. Let's just go ahead and pull up CFX here. Take a look. I think I have one of them opened. Yeah, so here's Mach 0.5, I think at 15 degree angle of attack. And so that, looking at pressure on the wing. So that's low pressure, which means high speed. So you can imagine there is probably a vortex over there. It's the high pressure lower surface. So there's all kinds of ways you can look at this. I think I've thrown in a few. I think I threw in a cross plane. So there's a plane where you can see what that thing looks like. And I guess you guys could do an animation where you scroll that thing back and forth if you want. You can kind of see back around here someplace, it starts to move away from the surface enough that has less effect. Another thing you might want to visualize is what's actually happening on the surface itself. I did this as a free slip solution. You're welcome to do it as no slip if you want. It'll cost you more. You'll have to do an inflation layer. But yeah, either way, runs about the same. The lift and drag coefficients are a little worse. It's viscous, not all that much different. But you can also do streamlines that are stuck on the surface. Has anyone played with those at all? Call it a surface streamline as opposed to a 3D streamline. So you can actually use the surface as the seed point for it. Yeah, it's on the canard, and tell it how many points you want, and then you can dictate how long they are. But anyway, you can see what the surface flow looks like it's going along there. So here's the big vortex. So you can see it's making huge cross flow velocities in there. And then this one, we didn't go to high enough angle of attack, but if you did in this region, this is where you're likely to see stall. So this is the higher pressure, so it's less useful to producing lift. Let's see, and then you can do exterior streamlines. So here's some streamlines that were seated just high enough. Like, that's where they were fed in. So I basically put in a line that was just a short distance above the leading edge of the wing as the seed point. And so they're pretty good at showing you the spin up of that vortex. It's a pretty fat core. And then you can see where it starts to separate from the wing back close to the trailing edge. That's where you get a little bit less use out of it. At lower angles of attack, you'll see that it remains pretty much attached. The lower surface is pretty boring. Much going on there. Just some outward flow along, kind of following the leading edge. Let's see, I think I have one other kind of seed the exterior of that the vortex. So this one starts to show you where you're reattached again on the center portion of the wing. So probably if you got up to about 30-degree angle of attack, you would see this start to fail here. This would, you'd start to see a separated pocket in the middle. Let's see, what other things can you do? You can also do plots of the pressure coefficient. So I think I did contour along the span with I think I did 11 contour lines. So there's 9 intermediate lines here, and then made polylines on all of those. And then you can go and do your CP plots. They look a little weird. This one out here is the tip. The chord is super tiny, so it's pretty minimal, but it's about what you'd get with a 2D wing. In fact, the outer 3 are pretty close to what you'd get with a 2D wing. But by the time you get to this pink one, you start to see this bulge, and that bulge just goes bigger and bigger and bigger. So all of that is due to that vortex that's stuck on the leading edge. Anyway, so a great way to improve lift. It's not without its pain. I tried to find some videos, but they seem to be vanishing from YouTube. So I didn't find any of the really good ones, but there's a couple where you can see some stuff. This is done in a water tunnel. We actually have, I'm paused, I can't quite read the logo on the side of the tunnel, but we have an idetics tunnel down in the basement of Halligan Hall that's looks like the same design. Ours is just about twice this big. But it's a great way for flow viz. So they've got this model stuck in their water. Water is going this direction, and then what they do is they have little tubes that they inject dye, just food coloring, into the water at various points. And so what they're demonstrating here, there's these vortex cores, and you can get this thing called vortex bursting. I don't know if anyone's seen that. I think he gets some cases here. So these vortex cores, they remain stable for some distance, but if the angle of attack gets high enough or the length gets long enough, they'll suddenly kind of become unstable, and they'll either just dissipate really quickly, or they'll go through kind of a burst. It looks like they're trying to get around a bubble at the back. I think you might get some angles of attack. Let's see. Yeah, so here's the non-bubble bursting, where the thing just sort of dissipates. Spot. Some of the other videos, I think, show the bursting better. This was actually a big problem on the F-18 when it first came out. The original A version, they would get these vortices peeling off of those wings, leading edge extensions. They go forward along the fuselage. And what was happening, the F-18's got the twin vertical fins back here, and the bursting was happening pretty close to the fins, but it could happen asymmetrically. So one side would burst forward, one would burst back. And so it was, I think, doing damage to the actual structural damage to the fins. But it also produced asymmetric loads on the vehicle. So NASA actually ran a huge number of tests trying to dig into the root causes of this with their own version of the F-18A. On the EF, I don't know if they still suffer from the bursting problem. The EF has another interesting feature that's also for generating vortices. The leading edge extension, fuselage, at the wing, and then got this called snag here. There's the fuselage. And the aileron was out here someplace. And I think the A, B, and C definitely did not have that snag. The edge was clean. When they went to the EF, the vehicle got super heavy. And they're having trouble where without the snag, the whole back half of the wing was separated. They have slots like all stalled. And so the aileron became basically useless when the pilot was coming in for carrier landings. And lateral control became really hard. So the snag is another vortex generator. So it's a huge vortex. Now you have this pocket here that's attached. Just enough to get use out of that aileron for the carrier landings. Yeah, and of course they've got a big giant vortex coming off of here as well, but it didn't reach out far enough to touch the ailerons. Let's see. I'm gonna do that. I want to share. All right, let's see what other videos did I save here. This guy's trying to compare paper airplanes to jets. I don't know what code he's used. Probably read the content. Oh, it's open foam. It's open foam. I don't know if anyone's ever played with it. It's a open source CFD code competing with Fluent, CFX, and everybody else. A lot of people really like it. I haven't tried it yet. So here he's showing the CP distributions that you could get. Let's see what else. I think there are some more flow bits. But here's the vortex bursting. And you can see it's frequently extremely asymmetric. So this is the place where you would get uneven load. And in fact, the video I was trying to find and couldn't find anymore. There's scenarios when a delta wing can, in fact, I think there's a CFD. Here's a CFD case of it. So if you take a delta wing and you let it roll on a ball bearing inside of a wind tunnel, and then just let the flow do what the flow is going to do, what you'll find is there's a natural wing rock mode for them. So this guy's trying to simulate it. I was trying to find some experimental videos, but they all seem to have either vanished or I don't know, YouTube's hiding them from me. So they'll actually get into this natural mode, and real aircraft will do that. Some of the early flight tests I saw with F-16, they actually ran into so high alpha, and the airplane would naturally go into this. Model aircraft do this all the time, delta wings, without some kind of stabilization scheme in there. Usually it's not divergent. It'll hit like a certain angle or a certain roll angle, and then it'll self-correct. Anyway, kind of a natural phenomenon. Some other flow viz of vortices, airstream. Anyway, this is about all I could find for a flow viz. It's a pretty common natural phenomenon, and like I said, it has pros and cons. From the missile perspective, the place where we win is that this super sharp diamond airfoil that we use for this problem, which would normally be useless as a 2D wing in subsonic flow, is suddenly really good in supersonic or in subsonic flow if it's swept, and then also works great in supersonic flow. I think I actually have a supersonic solution on it too. Yep. On the supersonic one, up to 15 degrees, the convergence of RMS values looks, let's say, believable. We can take a look at it here. When you get much higher than that, if you look at lift and drag coefficients, they converge great. Fantastic. But the RMS values don't converge all that great. And I think we'll take a look at it here, but you get such a huge expansion over the top of the wing. The Mach number gets quite high up in there and the pressure gets phenomenally low. And so I think there's some unsteadiness inside that pocket that the code is trying to resolve. And I actually ran one, I tried to keep this one small, so I think it's just under 500,000 points. I ran one that was about 2 million points and it converged better, but cost a lot more. So. So supersonic vortex is all gone. Doesn't show up. They get a little bit of a tip vortex, but it's pretty subtle. So the domain's big for Mach 4, but it's about right for subsonic. So I didn't want to make two domains and mesh twice, so just left it. The stuff out here doesn't cost you anything in supersonic because nothing's happening. It costs you a little bit. Not that punchy. But in the subsonic, it needs to be big enough. So let's see. So here we go. Here's Mach number. So 4 at the inlet. And down here, we're getting down to, what is it, just under 2. And then approaching 6 on the top. So you get some kind of interesting stuff. You try to figure out what's going on here. You've got like an expansion coming off the top. But because of the corner, the two expansions sort of hit. And so you get this like weird cross pattern here where the two intersect and reflect back onto the surface. If we add some streamlines, so here's surface streamlines. And so now, if you remember in the subsonic case, everything was like washing out to the tip. But in the supersonic case, it's the opposite. It's actually getting shoved toward the inside. And then on the bottom, we get a little bit of drift toward the outside. If you crank it up to, I think I went as high as maybe 30 degrees, and then you see a lot more drifting toward the outside. The exterior streamlines look really different. No vortex, and it pretty much follows the surface. What you'll see is this pocket back here will start to get a little bit bigger and bigger. It's just because the Mach number is getting higher and higher and the pressure is getting lower and lower. I think if we, let's change canard to pressure, you could see we're getting down. We're starting, I think free stream is 20 something thousand. We're down to 1900. And when you get up to 30 ray alpha, if anyone tries to go that high, you're down to like 200 pascals in that pocket. So it's getting quite challenging for the code. See, and I think I have streamlines into the bottom as well. And again, pretty benign. You can see a little more outward motion. You get away from the surface a little bit. Yeah. Anyway, so that's highly swept wings. So supersonic aircraft and missiles. That's why we do it. Yeah, in this case, I don't really see maybe a tiny bit of a tip vortex, not much. Yeah. Anyway, in the supersonic case, I don't think you can use the VLM method for anything, but in the subsonic case, you can. See, I think I have it in the expressions. coefficient. Yeah, so you can, you'll get these plots of lift and drag coefficient. And then what I want you to do is you'll run these 4 different angles of attack or more if you want. And then in Excel or MATLAB or wherever else you do your plotting, you can compute DCL D alpha and then compare that to the DCL D alpha you get from your vortex lattice method. So I think I have that here too. Hopefully nobody threw away their codes. Hopefully everyone's codes are actually working. So let's see, I think it's 2.8 aspect ratio, about tape ratio is 0. And then I think, what did I use? 40, I don't remember. You have to play around a little bit to figure out the sweep. Or a lot of you guys, I think, defined your sweep by leading edge, and the leading edge should be 55 degrees. I did mine with quarter chord, and in this problem, that's actually hard. I guess I could do the math externally, figure it out. Close. That's pretty close. So anyway, there's the VLM solution, and then this is the number that you want, the 0.0476. It's the CL per degree. And you can compare that against what you get out of CFX. And what that plot in Platzer's book hopefully showing us. Yeah, alpha. CL. And the VLM is going to be a constant. That's all it gives you. And then for this, I think I get something that's kind of like this. Degrees-ish, between 15 and 20. So there's this pocket where CFX actually over predicts VLM. And then eventually this, I think we're probably starting to see stall on the forward part of the wing. So it's starting to get full off. Neither of those 2 pieces of physics captured by vortex lattice methods has its uses. Anyway, so yeah, you'll do a plot like that. Only for the subsonic, supersonic, there's VLM doesn't work. Anyway, should be pretty fun. It's fun to push fun. But I think the physics is interesting. So. Just because it's so different from unswept wings. I think that's probably all the material we really want to cover for the class. I think if there's anything else I wanted to say on that. There are some other interesting things, I suppose, but they apply to missiles so much. We did talk about insects and their ability to trap vortices and the creases of their wings. You know what the Samara is? Maple seeds. I think some other plants that do it too.
One blade.
It's a 1-blade helicopter. So what I used to do when I first got here, I did first 8 years or something that I was here. I did super low speed unsteady aero. We were doing like flapping wing things. So we'd go to all these conferences that were kind of fun because they'd be a mix of engineers and a bunch of biologists, and they're all attacking the problem from 2 different sides. Kind of see some interesting stuff. So there's this Japanese guy who had made these model Samaras. He would take like a piece of balsa wood, cut out general shape, and then a chunk of clay here. It'd be like the seed. And then he'd try to model the shape, the average shape of ones that he would find in nature. He'd throw them and they would just drop like a dart. And so then he would go in and take thread and he'd glue the thread kind of like the little veins on the Samara. And then they would fly fantastic. And he actually got them to perform better than the ones in nature. And what they were doing is they were tripping vortices and the vortex would get kind of stuck. And as it goes out the end, it actually accelerates from the rotational inertia. And so it actually would help spin the blade up. It was, you get increased RPM, the better you made this. And so then another guy decided to turn this into an actual propeller. And so he tried making model airplane propellers that had this texture built into them. And it turns out if the Reynolds number range is correct, if it's close to what the Samarici flies at, it works great. But it seems like it's limited to a very narrow Reynolds number range that nature has chosen, and anything above there, then it's just useless. Let's see. What else? I think that's probably it. Yeah. All right, I guess we'll stop there. I'll be around Tuesday. If people want, I'm happy to come and talk more about homework 6 or 7. I mean, if anyone wants a walkthrough on it. Otherwise, you guys are free to just work on the problems and get them in. I think I mentioned I'm gone late next week, so I'll be gone Wednesday afternoon through the weekend. And then I'm here the whole next week, and then I think I'm have to go back to DC again on the end of finals week, I think. So if you're pushing your homeworks until the final deadline of like the 21st, I won't be able to give you too much feedback at that point. So get it done early. All right, good. Let's call it for the day.
We did a video where you tried to make one-bladed helicopters.
Yeah.
Like quadcopters myself.
Yeah, there's guys who try to make UAVs like that. Is that what
Really?
we're talking about?
I think so, yeah.
Yeah. So they have like one propeller, one blade.
Yeah.
Okay.
Counterweight on it.
Yeah, and then it's a matter of putting in periodic inputs,
Yeah.
depending on where you're at.
You wanna go this way, you gotta do.
So guys are trying to do that with multi-bladed helicopters too, where instead of moving the blades, they would just have, each of them would be motored, and they would change the speed of the motors. Because
Quadcopter. One blade.
yeah, it doesn't work great, but it does work some.
So just to be clear, the homeworks are due at the end of the quarter, they're not. No, well, I
Until
mean,
last year, fine.
because I can do it by next Sunday, it's just it's listed.
Oh,
When I sent it, but kept saying, but
so that's like the final drop dead too.
oh, okay.
I had been saying.
Thank you. So the due dates are the due dates?
I mean, if you're really pinched for time, the 21st, I think, is the drop dead date. Yeah.